encontró cuál es pues, y cómo está construida la URL. Entonces, una URL, descarga.
Ayer, bueno, como esto que te llaman la gente, ¿cómo me das eso? Porque lo mío era muy repetitivo. Y para, un punto de está muy repetitivo. Pero luego lo intento y no funcionaba porque había un poco salía. O sea, la página tenía un poco.
Sí, perfecto.
Solo tengo una cosa, yo tengo una casa. Pasó este año, ¿no?
Absurdamente.
Yo pago aquí 8 veces más impuestos al Alemania. Que en cierto país, porque para una casa, sí, para una casa como la mía, le pago 1.000.000. Aquí, ahora son 6 millones. Uy. No, 7, casi 7. O sea, tú pagas el 5% del valor por año. Es una cifra absurda. Y yo miro afuera y me pregunto, ¿dónde están las calles buenas? ¿Dónde están las estradas?
El video de catastral de Chía no es legal.
No, el problema, la verdad, no es esto. O sea, el valor puede ser verde. O sea, le pone una tasa de por mil.
Pero mira que, de hecho, el problema, porque me pasó con el estudiante que tuve dentro de ligar, si éramos nosotros. Porque construyeron un modelo que hacía la predicción del incremento de la valor y el condenado modelo era una regresión lineal simple, que entonces cogía predios que pues
Unos caros.
de referencia, exacto. Entonces, la regresión se disparaba porque había ciertos valores atípicos y entonces le disparaba el predio a todo el mundo de la misma manera. Le decía, venga, si la dinámica es geográfica, si estoy más lejos de la vía, si yo no tengo el centro comercial cerca, a mí por qué me van a incrementar lo mismo.
No, pero lo que pasa es que si tú ves los valores que ponen en el catastral, en Chile corresponden más o menos al valor verdadero del mercado en este momento. Sí, eso es correcto. Pero lo que pasa es la tasa que se aplica. O sea, a mí me parece absurdo por año el 1% del valor de una casa.
El modelo que aplica ese incremento es una regresión simple, que no tiene sentido porque no te deberían aplicar la misma tasa a ti que le aplican. O sea, ¿qué es lo que está pasando? Hay predios que pues, son de, no sé, 400 hectáreas que no están pagando casi nada, cuando productivamente ya se sabe que deberían estar pagando. Pero el lío es que hay al otro lado, pues, un pequeño campesino que tiene una casita, no sé qué, y a él también le incrementan porque, pues...
Pero entonces ahí puedes incrementar el valor. O sea, una cosa es la tasa que aplicas y lo otro es el valor de base que usas para eso. Pero esas tasas que usan, empezando con 7 por 1000 o 5 por 1000, una cosa, esas cifras son simplemente altísimas. O sea, una cifra de 5 es altísima. La otra pregunta es, ¿qué es el valor estimado? Eso lo puedes ajustar también, eso es lo que ustedes hacen. Pero si tienes un valor verdadero, imponer un 5 por 1000 anual sobre esto o hasta 1%, esa es la cifra absurda. Entonces, para mí, el problema es más la ley que implica esas tasas. La manera como calculas el valor. Eso puede ser otro problema en algunos casos, pero porque tal vez esa valoración tal vez no es correcta, no sé.
Lo que pasa es que en Colombia tenemos un problema que no hay en casi ninguna otra parte del mundo. Aquí tenemos dos entidades para manejar ese tema. Una cosa se llama registro, notaría de registro, y la otra se llama catastro. Y son diferentes, son independientes, y una no implica la otra. O sea, tú puedes ir a vender un inmueble, registrar una notaría, pero nunca ir a registrar la catastro. Entonces hay una brecha entre los valores en desorden, no sé qué. Cuando me he sentado con mis personas en otros países, me preguntan, venga, ¿y ustedes cómo arreglan este problema? Y dicen, ¿ustedes por qué tienen ese problema? Si nosotros aquí somos una sola entidad. Catastro, registro, es una sola. En México, en Corea, pues, hicieron el problema. O sea, ¿y saben dónde viene el problema? De las colonias. O sea, cuando
Eso iba, porque es que
porque un sacerdote de turno en algún momento dijo, usted va a manejar esto y se lo dio a un rey, no sé qué, o sea, para darle contentillo a los dos, la historia es más o menos, y se quedó así. Y entonces cada uno comenzó a manejar por separado los temas, uno para dar fe pública de que viene el reino y el otro para manejar los impuestos. Y cada uno comenzó a trabajar por su lado y al fin no se y hoy en día estamos. Pero hoy en día no
Con esa historia, pero es porque
¿Cómo?
ya tienes escuelas, ¿cierto?
Sí. No, o sea, yo cuando voy a las conferencias, soy de liga, igualito.
Pero pues digo siempre me dicen, ay,
Yo también digo, yo trabajo en investigación, en catástrofes. Estoy tratando de arreglarlo, estoy tratando de construir un modelo que sea un poquito más.
Okay, so very good. So we stopped last time. We stopped here with this formula, saying that we can compute the internal state for after token k using this matrix A bar to the k times the initial state. So we have the initial state projected with a number of matrix multiplications, okay? And then, or let me go immediately to this representation. So with this times, then we have a sum that goes from over all the inputs from the start to the last token, and we multiply with this convolution kernel matrix. But the problem is that this matrix is a different one for each token. That makes the computation a bit cumbersome. So if we think maybe a bit in a figure, let me go back, we have this figure, because there is a lot of math going on. But in the end, what we want is that, or a formula that allows us to compute the internal state at some point of time only in terms of the initial state. So here on this border, you would have this A bar to the K, okay? And then you take into account all the inputs that have arrived until that time, and this is what you put into the sum. So you have to multiply the signal, the signal here with some matrix. So at this level, the math is simple. Basically just this value is this value multiplied with the matrix plus this value multiplied with the matrix plus this value multiplied with the matrix and so on, okay? So the only problem is that the matrices are nasty. Yeah? So it's not like that conceptually. Record the session. Also record. Not sure what happened. My Wi-Fi broke out somehow. Okay, so it's not like it's mathematically complicated or conceptually complicated. The complication is only that, I mean, we could do it in principle, but the problem is that this would be super slow here, okay? So this is where we need something. And this is, all of this basically was of the introduction. Because now we talk about the actual contribution of the 2022 paper. So we have this remaining problem, or that's the bottleneck. How can we efficiently compute and store all of these kernel matrices? Because remember, and now it's really, maybe I should write this down there. So what are these matrices again? So basically, we can say that the matrix K J bar, that this is this matrix A bar to the J times B. Okay. So this is not complicated, but again, if we have this to do this like 10,000 times, not so nice. So and we need 10,000 different matrices. Okay, so so the problem is that we have to do, if we do it naively, we have to do a lot of matrix multiplications. This cost, it has square costs at position J, and we have to do J times. So in the first place, it's only one multiplication. For J equals 1, it's only one multiplication, but if J is 2, then we have 2 multiplications, A times B, and so on. Okay, so this is where this J comes from, and the D square is the cost for one matrix multiplication. Okay, so and another problem here is that if we do it this way, even if in principle it's possible, this is not parallelizable, because we have to compute all these matrix multiplications in a sequence. Right? So this is a bit like in the recurrent case. Then we are not. And when you remember, the first slide last time was that we wanted to have both the advantage of the transformer to allow parallel computing and not do this sequential recurrence as in RMS, but we didn't want to have this squared cost in D, which we have in the transformer. So this is exactly what we do not want to have, because this would also what we would have in the attention mechanism. Okay. So this is then actually the contribution of this paper here. For me, this is in deep learning probably one of the most involved contributions, but it's certainly important to understand it, because this could be where everything related to sequence compression goes in the future. Okay, so let's simplify things a bit and say, after all, we want to compute such a sum here. So we call it GL of Z. So Z is the input signal. So that would be a bit here, the Z. Okay, we simplify this here at this point a bit, because it's not so important that we have different values for each K. But we say that this is the origin, that is some constant to the K. Okay. Now, the question is how can we compute this efficiently, right? This is our problem. So let's look at some other sequence, which is this one here, H of Z. Okay, so we basically take the same expression, but instead of going only to L, we go to infinity. And that looks like maybe not as an advantage at first sight, but actually it will turn out that it is an advantage. So then let's look at what the Kj is. In our case, the Kj is, I wrote it down there, it's the A bar to the J B bar. Okay, and then I see, okay, but the B doesn't depend on the J, so I can put this out of the sequence. Okay. And I put the Z in, so I can reshape this to this expression. And then funnily, this here can be written, this sum here can be written as in this expression. Anybody knows why that is the case? Actually, this is kind of, for computer scientists, this is common knowledge, basic knowledge, but that's not many here. I think nobody is a computer scientist. So, you know.
You mean why you can factorize the B?
No, that's trivial, like yes. No, why is this series that goes to infinity? Why can I write this whole series with all these matrix multiplications here? Why can I write this simply as an inverse of this matrix?
You meant term.
No.
So the something related to the magnetic vectors, maybe?
No. So let me give you the real valued rotation. Anybody has heard of the geometric series?
Yes. Okay.
Go ahead, please.
Okay.
Yeah. Shut it. Okay, so suppose that you have a that is smaller than 1, okay? Then this implies that the series that goes from a to the I, this series here converges. To what? This converges to 1 over 1 minus a. This is a super basic result in what is that? Analysis, or no, probably this is algebra. But I learned this in the first semester of my undergraduate studies. So this is a very, very basic result. And the point is that, so this is the same as 1 minus a to the minus 1c. And then we see, okay, actually that's exactly what we have there, except that we do not have a number here, but a matrix. Okay, so it's kind of generalization of this result to matrices, because this is kind of matrix of size 1 times 1. You can use it also for matrices of different sizes, and actually for the general identity, you don't even need this condition. So generally, you can write this identity here, even without this condition, only for this case, it converges. And otherwise, it's really just an analytical object that cannot be evaluated. Okay, so here we use then the geometric series for matrices to convert this into 1 minus, well, the A. The A is this product here in the inner, which goes then here. And well, in this case, I can have 1 minus 1. 1 over 1 minus a. If I have matrices, I can do divisions. There is no such thing like divisions with matrices, but I have an inverse, which logically and algebraically corresponds to the same thing. Okay, so that looks nice, because now I see, instead of having to sum up all of these matrices here, instead of having to do all these multiplications of matrices and sum them up, I can just do a single inverse. So that would be a huge gain. The problem is only that we do not have to compute the full series, but only up to here. So how can we get, so to say, only the part until L minus 1 and not the whole series?
Minus infinity is the same.
But the problem is that this here does not converge to 1. So we do not really. Yeah. So mathematically, you can say I want to compute, or I need to compute. I can compute this and then subtract the rest of the series from here. But this is not gaining anything, because then you would have to compute also an infinite sum. But then it would be even easier to compute this directly. So yeah, I mean, mathematically you're right, but this is not practical. Wouldn't be the solution that we want. All this here is about computational efficiency, because if we would say time doesn't matter, then we just compute it directly. Okay, so but this is the important starting point. Now, maybe we have to do a small. Yeah, is what I said. And now is where things get really funny. So we see that so these two are not the same, right? So this here is not the same as that, okay? But we will find a way to make them identical for specific z's. Now let me do a quick excursus, because so I know that some of you are familiar with the Fourier transform, but not all of you, maybe. So we can look at the number e to the minus I to p n. So what is this? Anybody knows what is the x, or the e to the minus I? This is the imaginary number, right? So this I is the square root of -2. No. Yeah, you're right. -1. -1. Yeah. So I squared is -1. Yeah. Thanks. So anybody knows what I get when I do this evaluation for any values of n? No. No. So this is something that really has fascinated me in math. So this here is a cyclic function. So what you get is some point on the unit cycle. Okay, so here we have the 1, and here we have the 1, and what you get here for any n, you get no matter whether it's negative or positive, for any number you get some point on this circle. Okay. Same. It's the same. Not exactly. So this here is, but they are closely related. Yeah, so this is called the Euler function, and it's basically the cosine of the angle plus the sine of the angle. But yeah, in principle. But the important thing is this cyclic property, that no matter which value I put here, I always land on this circle. Now, one important trick, and this is what the discrete Fourier transform does, is that you say, for these values of n, I want to do something special. I want to do so 2p is a complete turn in the cycle, right? So, I mean, let's look at what do we get if we put n equals 0? If we have n equals 0, then we end up in e to the 0, which is 1. Okay, so that would be here. Okay, so we start here.
Actually, what is the another point? When x equal to 0, okay, okay, that works.
Anyway, after all, it's just a transform. And now the point is that what happens if I put n to 1? If I put n to 1, I basically did a full turn in the cycle, and I'm again here. So for every integer value of n, I have a complete turn. So actually, I only get different values for n in the unit interval between 0 and 1. So that could bring us to the idea, let's define this as something like a fraction j over L, where this tells me on which portion, so I want to have L points in total, and they should be equidistant. So if I have, for example, L equals 8, then I would have this point, this point, this point, this point, this point, this, and this point. Yeah, because I start with j equals 1 and I go until L minus 1, and that would give me this point. So I get kind of equidistant distribution on the unit side. Good. This is what we will use now. Okay. So when we have an expression like this, e to the minus I, then this gives me always points on the unit circle. This here is only to say I want them to be expressed somehow in terms of complete cycles. And here is the portion of the complete cycle that I want to cover. So the magic is, okay, so this gives me actually this here gives me complex number, right? Complex number. But the complex number is, I can think of complex numbers as points in a two-dimensional coordinate system. So if I put a 0 here, I get the real component 1 and the imaginary component 0. This is why I'm here. Yeah, because this here is the real component, this is the imaginary component of the complex number. Yeah, and this is why putting a single number, a single like natural number here or a rational number in this representation gives me a complex number. So I will have complex numbers here, but better or yeah, it's better to think of coordinates instead of complex numbers. And this is exactly the idea now. So we say, let's look at these two functions, g and h, only for specific z's. The z's are zeta, we call them zeta j, and they have exactly this definition. This is exactly what I wrote there. Okay, so we have e to the minus I 2p, and then we have this fraction j over L. So 2 minus I implies that we will be somewhere on the unit circle. 2p means that we will think in complete circles. This is like our basic understanding. And then here j over L is the portion of the whole circle. This will be a number between 0 and 1. Okay. So far, so good. Now, if we do this, then it's clear that if we say we have some z to the k, and we add an L, so if we just, if I add L here, then basically nothing would change. So if I have a point here that is the result of some j, and then I look what happens if I don't have j but j plus L, then I will just get one complete round, and I end up here again. Okay. So that means in this function here, if these are my inputs for functions, then z to the k plus L is the same as the z to the k. And this is, I don't know exactly when that was invented as a trick, but that will be super useful now, because if we evaluate h on these points, we only can get L different values. So for this type of z, this is not in general, but if we say, let's only look at these input z that have this property that we construct like this. So the definition of h was this. It's this infinite sum, right? And now we can say, but wait, for this value z to the k, there are only L minus 1, L different possible values. Yeah? So it's like for k equals 0, basically we are here. For k equals 1, we are here. Then we get here, then we get here, then we get here. But once we have seen L values, then we again start to see the same values. So k can go to infinity, that's not a problem, but the z to the k will be exhausted after L steps. There will not be more different values for z to the k. Clear so far? So that means for this value here, I have an infinite sum, but for this value, z to the k, there are only L different values that I will see.
But that L still could be infinite, right? Because it could be like any point in the circle. Maybe. How is that an advantage? Because still, like the circle has infinite points.
Yeah, but but we do not visit the whole circle. I mean, we do not scan the whole circle. We know that there are these 8 points on the circle, and we only look at these discretely.
Okay.
So basically, we iterate discretely in a sum only over these points here. In theory, we have to do it an infinite number of times, but basically we're now doing a factorization. So we're saying, okay, there are only 8 different values, for example, in this case. So let's go over these 8 different values. Now, but each of them needs now to be multiplied with all the times. So yeah, I see this point here infinite number of times, and I have to multiply this thing with all these sums of these, with all these KK matrices here. Not only one, but all of them. This is then the factorization that we get here. Yeah. Okay, good. Now, when we look at what this z is, this z is some, yeah, it's now e to the minus 2 pijn over L. Now, because the n just gets multiplied into this to the structure. So this is exactly what a Fourier transform is. As a discrete Fourier transform. In a discrete Fourier transform, I have some number. Think of this. This is just some number, and this number is being multiplied with an exponential of e to the minus 2 pi. This is exactly what a Fourier transform does. So what they say is that actually, if we compute this here, and we can compute the full series can be computed with this trick. Yeah? This is not what we wanted after all, but essentially this corresponds, if we do it for all these values for all these L values, like for each of these red crosses, then this is the Fourier transform of these input values. So we can think of this where what does a Fourier transform do? So just to a discrete Fourier transform. So if you have an input signal sequence of lower letter x, oops. So what a Fourier transform does is it converts this into a new sequence where xi is that I have to go over all the to n. So the ith entry goes over the full input sequence and takes this value and multiplies it with e to the minus p I and then the j over n. Okay, so this is exactly the formula that we have there. So we are computing a Fourier transform where the xj, this number is this series here. So this series goes here. This is my, so to say, here my x1, and this is the x2, and this is the xl. And over these inputs, I compute implicitly a discrete Fourier transform. So this I can do. So what I can have easily is the h of z. But remember that we didn't want the h completely because it goes over the infinite sum. So computing this is easy and cheap, but actually what we want is only this, the k0 until the kl minus 1. So what we can then do, if we know that this is the relationship, we can take these results that we computed here and to compute the inverse. So the Fourier transform also has an inverse. So you can say, so I don't start with these values and compute these, but I start with these values and I compute these. That's the inverse. And if we do this, then basically we recover here these values. Okay. And then what they say is, okay, so we now assume that if this value r here, if this is bigger, at least 1, then we are already having basically a matrix that is close to 0. So what they say is, this is kind of assumption that this series here is just equal to k0. And the next one is equal to k1. And this series here is equal to kl, because, kl minus 1. Because as soon as this here grows bigger, I have exponents that become so large that the matrix here converges to 0. So they identify this series here just with k0, and this here with kl minus 1. So this is how then they compute these matrices that we want to have. So long story short, instead of doing all these matrix multiplications, they say I just do an inverse. The inverse allows me to compute this value h of z, but I have to do it for several of those. So I compute the result vector here of this, and I apply an inverse Fourier transform to this to get my actual matrices k, j, kj. Yeah, that. So we trade a huge number of matrix multiplications by one inverse and an inverse Fourier transform. That's the trade here. Now, one could say, okay, but computing inverse matrix is also nasty. So maybe this is not even so much better. Yeah. So mathematically we can get that, but is that even better? So, and here's then where they apply the next trick, saying that we assume that this matrix A bar is diagonal, in the sense that we can write it as a diagonal matrix of eigenvalues plus an outer product of two vectors. So if this here is a column vector, P is a column vector, and Q is a row vector, then P times Q transposed gives me a matrix. So if I have a row vector times column vector, this is a dot product. This gives me a number. If I have column vector times row vector, that gives me an outer product, is a matrix. This is a matrix, where at position ij, I have the product of the value I here and the value j here. The point is that such a matrix is low rank. That means rank 1. So all of the columns in this matrix are linearly dependent. And matrices that have this property can be, well, first of all, I can do this multiplication super easily because computing an outer product is very easy. But they also have very nice properties here for computing inverses. Okay, so this is a kind of assumption they make. They say, because after all, I could have an arbitrary A. Any matrix A models one of these differential processes. They now say my A must be of form that I can write it like this. So one would think that this eliminates many possible models for this differential equation system. And I'm still not completely sure how strong this assumption is, but well, apparently many people are very happy with this and it works very well. So you say, in theory, I could have any A, but if I want to make computation efficient, then I should request that my matrix A follows like this scheme. But for computational reasons. And then I pray that within the set of these types of matrices, I can learn something useful. But apparently it's the case, because if you look at this paper, the results are really, really impressive. So I'm not sure whether we get a chance today to look at that, but just to give you a number. So there is, at that time, like 3 years ago, a very difficult benchmark for long-term dependencies and sequences. They have like 8 problems or so. And like all these other methods, like, I mean, they didn't even check recurrent methods, but or LSTMs, but they checked transformers, and transformers have a score of, they reach a score of something like between 30 and 50 on the different tasks of 100, 30 or 50 of 100. And with this, they went from 30 to 60, from 50 to 80. So the jump is really huge, much higher than in all of these other, I mean, the improvement is much better, like from transformers, from LSTMs to transformers, for example. So apparently it works really, really well. Good. So if I enforce that my A bar is of this shape, then I can do the inverse pretty effectively. And it looks a bit nasty. But what they apply is the Woodbury identity that defines, this is a result from, I think, from the 19th century even, that explains how I can write the inverse of a matrix in a specific way. Okay, so they just use this result and find I can then write this inverse here. So I replace this A bar with this. Okay, then I get this result. And then using the Woodbury identity, I get something like that looks like this. So this looks super nasty. But the point is that this matrix that we have here, dz, this is basically I minus z lambda. And this is a diagonal matrix only once. And lambda is also a diagonal matrix, and z is a number. So this here is a diagonal matrix. And if I want, for example, to convert to invert a diagonal matrix, that just means I have to compute the reciprocal of all the values on the diagonal, right? So, quick example. I have maybe a matrix that looks like this: 1, 2, 3. So that could be such a D here in this case. Now, what's D to the -1? Well, in general, if you have another matrix, then computing the inverse is nasty. But here, it's just like this. Okay? Because you have to compute the reciprocal of all of these. This is trivial. So, and now we use this inverse 4 times. Here, 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 and here. And P and Q are also only vectors. So syntactically, this looks super nasty, but it's just a bunch of very, very cheap operations, which eventually then makes this whole thing feasible. And now more. Okay, so that's one thing. And the other thing is that you see that here at no time we use the J. So we can compute this. We can compute this for all of the steps, for all of the red crosses simultaneously. So there is nothing like we have to first do 5 matrix multiplications and then the 6th. So this recurrency goes away with this trick. And that means that if you, for example, have 1,000 or 10,000 time steps, you can compute for the 10,000 time steps in parallel this term that you need for the approximation. If you have 10,000 CPUs. No, but I mean, you don't have 10,000 CPUs, but even if you have 8 or 16 CPUs, then I mean, this is a tremendous speed up that you have if you have to compute this whole like batch of tasks. Okay. I would personally, I haven't implemented this yet, but or I haven't used this myself, but I still would believe that it's still, even with this, rather expensive. But yeah. Now, how should this be initialized? So in theory, you could just do something random here. You could just say, give me random values for this on the diagonal, and here also random values. But those guys showed in a previous paper to that it's good for this kind of problems to use a specific matrix, which is called the Hippo matrix. Okay, so this is for actually, I have to admit that I forgot the exact name, but one of the pieces here is for polynomial approximation of polynomial optimization, polynomial approximation optimization, and the highest, I think, a hybrid or so. And I also don't know exactly the details why this makes sense, but if you say the lambda, I just put on the, I only have diagonal values like there, right? So I have in the beginning of -1/2, then -3/2, then -5/2. So it's just like minus, and then like the row where I'm at -1/2. So that would be like the initialization for the lambda, and for P and Q they suggest like these two formulas, which are basically the same in this case. So we just have like, we would square these values and then just get 2i plus 1 and 2i plus 1. That's it. So that would be the initialization. Okay. And this, of course, that is our first candidate for a prop. That doesn't model anything useful for us, but they found that initializing with this instead of something random is somehow very useful. I guess there are also theoretical arguments for this, but this is where it starts. But this is only initially, and then these are the matrices we learn. So these are actually the parameter matrices. We have we learn the diagonal for this matrix, and we learn these two vectors. This is all we learn. And then the A is implicit. Okay, so let's sum up. So we want to use these differential equations because in principle, if we have these matrices A and B that model differential equation process, we have infinite memory. It's not about saying that we believe that the true input follows exactly such a model. That's not the point. The point is that we want to have some component somewhere in a block that has infinite memory. We don't want to model it maybe with one single such component, the full process. It's just we want something that has infinite memory. Yeah. So with this, I want to say, so don't get confused. It's not about saying maybe we have an input signal that does something like this. And now we want to use such a process to model exactly this behavior. It's not about that. It's to say that we want, let's say, so that is the true curve. Maybe we want to have two such units, memory units, and one memorizes this. And the other process memorizes maybe something like this. And then you say, if I combine this, with activation functions and linear projections, I can recover the blue thing. So it's not like we need one of these, like only one to recover the true signal. And besides, it's not even really for the blue curve itself. It's only, those are just our like hidden states, okay? And the idea is that we can represent this whole green curve and the whole red curve only through 3 vectors. And the vectors don't have this length. The vectors have some very short lengths, yeah, maybe length 10. So with 3 vectors of length 10, I can describe this whole infinite sequence of hidden states. Now that's the whole point of this. Okay, so now with respect to S4, S4 is stable state space. Don't ask me why it's called stable. I think it's a bit for numerical reasons because all of these matrix multiplications can introduce some numeric instability. So maybe it's because of that. But what they actually solve is this problem of, how can I avoid to have to compute this huge number or to have to do this huge number of matrix multiplications. So I don't want to compute this in a naive way. That's actually the contribution. So how can I do this computation efficiently? So I don't have to do this this kind of operation here, but I replace it by many, but very cheap operations, which do not even depend on the J. So I can also do the whole 1D convolution in parallel. And because this thing has infinite memory, then in principle I can, or at least, no, it should be, no, it's infinite memory. I can in principle have, or I can capture arbitrary long dependencies in my sequence. So I was not 100% convinced of this approach because I think you still have to do L inverses. Okay, so because you need L different of these matrices. So you have to compute L of these inverses. So to me, it still seems to be quite expensive, much cheaper than without the trick, but still rather expensive. Okay. And the other doubt that I have a bit about this is that we have a kind of, because of this decomposition assumption that you say you write A as lambda plus this low rank matrix excludes maybe a lot of possible choices for A and B. But it could be that this second thing is really not a problem because you just find something useful within the spaces of A and B that comply with this restriction. So it could be that this restriction is not so important. But this here is a valid point. And then there are new works from 2023 and last year and this year, which I think the latest is called Mamba, which improved this point here and make it even faster. Okay, so this is a very active field of research currently, this class of networks. And so this is the paper we've been working here. Okay, This guy, I think from this, he had his first publication in deep learning in 2019 or 2020 or so, and since then he has already accumulated like 20,000 citations or so. Yeah. So if you have a good idea, you can become very famous. The next guy that we see now, Ian Goodfellow, is also a candidate like this. I mean, I think during his PhD project, he published the GAN paper, which has now 85,000 citations. Yeah, so let's see whether one of yours makes such a contribution. Okay, but okay, so let's stop here. So questions about this, the state spaces. So basically, it's an alternative block to transformer block. So if the logic is, well, transformers change the world, and this guy outperforms transformers by large margin, maybe it would be good to understand that. Even if it's a bit complicated, technically speaking. So it outperforms it in two senses. So it has better performance because it has better memory, and it is cheaper to evaluate. So it's a win improvement. In theory, I'm not so sure how training times are in practice. Sorry with this. Okay. Then let's talk a bit about these guys here. So, since this was a rather complicated topic, involved topic, let's call it like this, I decided to do now something very light. Because the other next topic will be variational outweight encoders, which is again a bit heavy. Okay, so GANs, I think, I mean, I could have done a kind of bit deeper presentation here, but I think the general idea is relatively easy to grasp, and I want to keep it like this so that you do not get completely overwhelmed here. So this is now a completely different topic. Okay, so we are now closing this topic of sequence treatment. So what we start now is to talk about generative models. So at a very high level, the three most important generative models are the generative adversarial networks, which we see today, the variational outweight encoders, and the diffusion models. So what is a generative model? And in principle, this is also very funny. So when you talk about generative deep learning, then people think of GPT and content production, but this is not correct. So generative models are not models that generate text or sequences. The generative models are models that allow you to sample from a distribution. This is what is because so they can generate new data. This is what is meant with generative models, not that they produce content, but they allow you to generate new data. So what a generative model is a model that learns a probability distribution over data and can generate new samples from that distribution. That's a very simple task. So, for example, I mean, a very, very simple example, and maybe this would be a great homework exercise. So you think of a dice, but a biased dice. So you do not get every number between 1 and 6 with equal probability, but with, well, different probabilities. And now what you have to do, so I'm showing you results of this dice. And what you have to do is to create a machine that then can create new examples from the same distribution. Yeah. So let's say I'm the owner of the distribution of key data, okay? And you don't know this distribution, I know. And then I sample from this, I sample values. So we have a 1, we have a 6, we have another 6, we have a 3, and so on. So we create a number of samples. I create a number of samples. And I only show these samples to you. And your task is now to learn what this here is, and then replace my sampling mechanism. So you basically replicate or synthesize a sampling mechanism for this. And this is, of course, super useful, because if we were able to do that, then we can basically generate an infinite number of training examples, new training examples. Right? Okay, so this is then the data set that is the input, and the general model takes this and learns some parametric distribution, P theta, such that these two distributions are the same. So let's think of densities. So the density of the density I estimate for any x should be the true density for that x. That's the idea. Okay. Okay. So for the rest of the course, we will look at models that do something like this. You don't see labels here. So this is not a supervised task. But there exists a supervised variant, which is then a conditional generative model. Okay, so then we can even create labeled data. But right now, that will be next week. Okay, so today let's just look at the axis. Okay, very good. By the way, if you want to have, I mean, if you have a column that you consider as a label, I mean, it still works. It's not the point. But in this case, you sample the X together with the label, like alongside. Okay, but this is not a conditional. It's not a kind of label generator for certain instances, but I just generate a complete instance. So I'm not saying that you cannot use it. So, for example, in the case of iris. Okay, you could say I have 5 columns. So my X consists of 5 columns, which are the 4 basic attributes and the label. But I don't treat the label specifically. I just say I sample everything together. Yeah? So I'm not saying that you cannot sample the labels, but they are not treated specifically. Okay, so this is this is the eventual objective. I want a generator for date. Okay, so the very high level idea, I will also have a figure, but let's see what the high level idea is, or how could I do this? So I want to estimate this here through a functional network, so a deep network. Now we don't make any assumption about the structure of this here. It doesn't really matter. And what this network receives as an input are just random inputs. That looks super strange. So let's say you do a fully connected network with 100 input neurons, and what you put into the input are just random numbers between 0 and 1, for example. So you don't put actual data there. It's maybe completely unclear at this point why you would do that. But so you define, you have a noise distribution. Typically, it's a uniform distribution on 0, 1 or something like this, and you sample vectors from this distribution. Okay. And now, but the network G itself, and this is why it's set here functional, so this is deterministic. And if the network G for generator, okay, G is the generator. If this is a deterministic network, then how can this create something new? You always get like the same, for the same input, you get the same output. So what we want the input to be is some kind of So if at the end this should be something random, then what the input should be something like a random seed. So once I have a random seed, the sequence of what I generate is deterministic, right? So G is, so to say, a kind of pseudo random number or pseudo random object generator that is in itself, it's deterministic, but we bootstrap it with a random seed. That would be a very good way to think about this. Okay. So what G must somehow learn is to map these random seeds to something reasonable, to reasonable objects. For example, you put in a noise value 0.3, and it should learn to say, okay, that is dice result number 5. So it would map every number in between 0 and 1 to a result between 1 and 6 for the dice example. So maybe I could say G of 0.3 would be 6. G of 0.29 would be 3. G of 0.8 would be 6 again. Something like that. Okay, so the output of the generator must be something of my space. And it's only influenced by some random input number. And the idea will be now, well, in the beginning, we start really with, so the generator will not have access to true data. So he will not see this data that I sampled before. So I roll the dice n times, that gives me the database, but this network has no access to that, and he cannot see it. What he can see, or what he will learn from, is that there is another network that takes his output. So what we will have is that we have another network D, which is called the discriminator. And he will see true results from the dice from I rolled, but he will also see results produced by this guy. And the point is that he doesn't know whether. So I show 5 to him. So I tell him, I give you a 5, and he should say whether this 5 was generated by the true dice or by this guy. And that looks difficult. So he will give a numerical output here in terms of probability. So this is a binary classification problem. He is to say this input belongs to the true distribution or to something that the generator created. Yeah? It's a binary classification problem. Where does this come from? From here or from here? So, and the yes answer is that it comes from here, and the no answer, so that this is a fake number, is that it comes from here. And he has a probabilistic point. So he says he outputs the probability that the input comes from the true distribution. Okay, so if he outputs something close to 1, then he's saying, I believe that this is coming from the true distribution. And if he outputs something close to 0, he says, I believe that this is fake. This comes from, so the probability that it comes from the true distribution is close to 0, but that means that it comes from the generator. This is a simple binary classification.
But what defines the threshold to consider?
There is no threshold. He just outputs probabilities. So he does not answer yes or no ever. He just says that's a probability. I believe that this is true.
True based on probability number. So you need to decide if 0.8 and upper is true.
No. So what we do here is that we compile a database. So say here we have an X and here we have a Y. Okay. So what we do is that we get numbers 3, 1, 5, 5, 1, and so on. Now, some of these, we do this with a training procedure. I will talk about this later, okay? But since you already asked, so we have a training procedure that generates these the sequence, but the training procedure asks some of the instance from here. So then we have a one, and maybe here. But for some of the instances, he draws from here. So it's like he has two bags. And he always takes like one example from the one bag, and this is where he puts the one. And where he puts a 0 is where he took an example from the other bag. Now this is the ground truth label that we know, but this molecule will not have access to it. So he will just predict the probability that the true answer is 1. And then we can compute cross entropy, like always, between this probability here and true label. Okay, so the general idea will be that. So we have two networks, the generator network and the discriminator network. The generator receives random inputs that we just generate on the fly. So it's like, if I want to have something from the generator bag, so that would be this value, how do I do this? I generate a random seed. I put the random seed into the generator model and the output is my value. Yeah. So to get this pi, for example, I say, okay, I take a random value between 0 and 1. Yeah. For example, 0.85. And then the generator network maps me that seed to the 5. For some reason, we don't know how this happens. And this is the value I take.
But why is it important to randomize the?
Yeah, if you don't do this, what would you use as an input for the generator if you don't have it?
Can I use a constant number? For example? Oh, well, no, I got it. Yeah.
Yeah.
No worries.
Yeah. You can use a constant number, but then the generator always gives the same number.
Exactly.
So how do you define like the first layer, and why should it have like more, for example, for the iris test, like why would you maybe generate, I don't know, 5 different neurons as random instead of 10 or 20?
Or I can tell you. So I mean, I'm not an expert for this, so I don't know which configuration has which implications. I've not worked with guns myself. So in theory, there is no restriction. You can do whatever network you want. Now, what are the advantages of, or what is the effect of choosing more or less input or output neurons? Okay, sorry. So output neuron is defined by the space in which you want to sample, but at an input level, I have no clue, honestly. So I would believe it doesn't even matter. Probably you can really just take a single neuron even. And I'm not sure whether even at the mathematical level there would be any difference to having multiple input. What you need are multiple hidden layers. That's for sure. But once you have a random input, single input neuron, you should be able to blow it up to whatever you want afterwards.
Okay.
But maybe if you have several, it's kind of the question is a bit: do you want your value at the end only depend on a single random number or multiple random numbers? And somehow there could be a bit more by diversification if you have more random numbers. But purely mathematically speaking, it should make really a difference. But I'm sure that in practice it will have an effect. Okay, so that's the generator, and then we'll trade our samples. But of course, we have the true database as well. Okay, so then what we have here are the two bags to compose a data set for this guy. So he will see a binary classification problem with instances from the true bag, which is for him the positive class, and instances from this bag. But of course, he doesn't know for each of these instances whether they came from here or from here. So these are called true samples and these are called fake samples, because one way to explain this is like he's a kind of frauder and he tries to falsify money bills. So this is an example that I found really funny. So one example is that you have a true bill of money, like $10 or so. So this is here, and he should learn to generate pictures of dollar bills as well. So that's his goal. So here you have fake dollars and here you have true dollars. Yeah. So here, what he starts from is a complete mess. So when he does his first forward pass, you basically get an image that is only like noise pixels, nothing else. And then miraculously, over time, he will learn to produce images of dollar bills without ever having seen a dollar bill, not even in the training data. Okay, so how does this work then? So he gets these samples from the two different sources with the two different labels, positive for here and negative for these. But of course, in the forward pass, I don't see the label, only later in the loss computation. So once he made a decision, I get two losses. Loss for this guy here to update him and a loss for these. So the learning process here is really a bit different than in other networks, because here we have two independent forward passes and also two independent backward passes. So it's not like we're doing one forward pass and then back propagate and simultaneously update him and him, but it's like we're doing only forward passes for him up to here. No, we're doing forward passes here and first update only the discriminator. And once we have this, then for this guy being fixed, we do forward passes from here and update the generator. So it's happening like in two phases. It's not like in one forward pass, we compute a loss in the end and then update both models. Doesn't work like that. So how does it work? What's the loss function? So what's the basis for the loss function? What we want is these two are two players in like they are competing. So he tries to falsify something and he tries to detect whether what he gets is true or false, right? So, okay, so these two are like somehow competing in a game. So they are adversaries. That's why this is called adversarial networks. Okay, so his job is to make sure that he's not able to tell whether his output is true or false. That's his job. So he wants to create like a false dollar bill that looks so real that he is not able to say whether it's true or not. Yeah? And he wants obviously to do the discrimination. So how could we define a loss function that achieves exactly that? So the idea of the loss function is based on the discriminator. So for the discriminator, so we have two types of instances. We have the instances from the true distribution, yeah, so that would be those above. Okay, I want for all of those that come from this distribution, for all of those, I want that the probability assigned here by the discriminator is 1. Yeah, because the output of the discriminator is the probability that the input was authentic. And if the input is authentic, I want that this guy outputs a 1. Because if he outputs a 0, then he thinks it's a forgery, and that would be wrong. So I want that the discriminator here outputs a 1. If he outputs a 1, then the logarithm of 1 is 0, so he doesn't have a loss. So this is basically entropy, cross entropy loss, right? But for the binary, so it's log loss, yeah, for the binary case. This is for the true instance. What is for the false instances? So what is for the z's, the instances that come from the from the generator. For those, he should detect that they are wrong. So if I get now an output from the generator, so look, this is a true, this is an authentic input directly from this, and here the discriminator gets an input from the generator. So if he gets something from the generator, he should ideally say what? 0. Because 0 means the probability that this is authentic is 0. So if he says 0 here, then we have log of 1 minus 0, which is 0 again. But if he gets a forgery and he says 1, then we have log of 1 minus 1 is 0, it's minus infinity. So the discriminator wants to maximize this number here. Okay, he wants to maximize this number or minimize the negation of that. Doesn't really.
That's expected value, right?
Yeah.
And how do we interpret the minus infinite the expected value of minus infinite case?
No. Wait. So it's not like the expected value is infinity. I'm talking about a specific x or a specific z. So if for a specific x here that is true, I produce a probability of 0. So I think this is for sure it's a fraud. Then I get log of 0. This is minus infinity. But this is for one specific x. Now, of course, the expected value. So the question is still justified because since the expected value is linear, if there is a positive probability for something of having minus infinity or plus infinity, then the whole thing collapses. So what you do in practice is that you don't really take the log, but you say you cut this off somewhere at minus 10 to the 10 or minus 10 to the 15 or so. You cut this off so that this cannot go to infinity for real.
Okay.
But this is a common thing that you also do in cross entropy. So there's nothing specific here, because you always have this problem with the log laws. Okay, so the discriminator tries to maximize this whole thing. But it depends on both, right? So it depends on the discriminator and the generator because the generator enters here. The generator only enters here. So this is not the loss function. This is the basis for the loss function. But for the discriminator, this will be close to the loss function, but clearly for the generator, I will not want to use this. So here I only optimize the generator in terms of what the discriminator later does with his outputs. Okay. So the generator tries to minimize this because because he wants the generator to be unable to do this separation with. Okay, so this is a function that the discriminator wants to maximize and the generator wants to minimize. Okay, so this is kind of minimax state. And this idea of the minimax state is also important for the proof. So how is the training procedure for a gun? So we are in so this algorithm here basically describes the train cycle. Yeah? If you go over the batches and invoke the model, so how would you have to implement this in PyTorch? Because this is not the standard. I think it's the first model we have that is not just like do a single forward pass, compute the loss, and do a backpropagation. So here it really works a bit different. So what we do is that, so in the first phase, which is this here, we only update the discriminator. So to update the discriminator, we do two things. We sample data from the true distribution. Also, we sample data from here with our, that would be the iterate. In PyTorch, I would implement this, if you can, as an iterable data set. So you have a stream of instances, and the instances come from some true finite set that you have available, okay? So this is like your first bag. And you also sample, you get samples from the generator, okay? So we don't, so this happens here. No, this is only the, this is only the input for the generator, and then we put this this stuff here into the generator and produce the fake. So we have two types of instance, X, X fake. And from these two types of samples, these are from the two bags, I can now produce such a table for myself. Yeah? Okay, so and once I did this, now I do a forward pass through the discriminator with these samples, and for each sample, the discriminator decides that is authentic or this is a fraud. Yeah, true or false. And then based on this, I compute a loss that is exactly the formula that we had on the last slide, only now without expected values because it's on concrete instances, but on average, we maximize the expected value because on average, every sample X occurs exactly with the probability it should. Yeah, and this way we optimize the weights in the discriminator. So what is important if you do this in PyTorch is that you use this detach option because you compute the samples here. So using G, the generator becomes part of the computer. So it's basically here a forward pass from here. So I do this and I do this simultaneously. I compute the discriminators and now I want to update the weights here and do a back propagation. But I don't want to be updates here, weights in this guy to be updated. So when I do the forward pass, I detach this guy so that no gradients will be computed for the generator at that point. So that in the backward, when I have the loss and I do the backward, that only the weights inside of these will be updated. Okay, so I use the generator in the forward pass, but with detached, with no gradient computations, and it will not be updated in the backward. Okay, so that is up to here, and then, and now I want to update the generator. Yeah. So to do that, I do a forward pass to the generator. What do I need for that? I only need to generate some new noise. Then from the noise, I generate outputs, and the outputs I send into the discriminator. So it's basically the same. So it's basically the same run. I go here, but now I disable the gradients in this guy. So here I will not compute gradients in the forward pass for him. So I do the same thing. I compute the generator loss, and now I do a back propagation, but the back propagation will not update anything here, but only here in the generator and not in the discriminator. Okay. So then this is a kind of a 2-round game. In the first round, I update the discriminator, and in the second round, I update the generator. And then again, the other way around. And this continues until forever. The log that I optimize for the generator is only the second part here. So you can see that, so what the generator wants to do, he wants to minimize this expression here, okay? But here, this term doesn't influence him. And the generator has no access to the axis, so it doesn't really influence his decision. So he wants to minimize basically this term. And you can see easily that minimizing this here is the same as maximizing this. So you just take basically you take the one out and invert this the sign here of this output of the discriminator. And it's also somehow intuitive to do this. So what does the generator want to have? The generator wants that if his output goes into the discriminator should say what? From the generator viewpoint. What would be a nice result? Well, a nice result from the generator viewpoint would be that the output of D is 1. Because that would mean that the discriminator believes that his forgery was authentic. Yeah. So if this guy outputs a 1, then again we have log of 1 is 0. Okay, and that's good. I would say, but why is 0 good if I want to maximize? Because if it's not 1, if it's not 0, it's even negative. Because if this guy outputs something smaller, like 0.5 or even 0, then the logarithm of 0 is minus infinity again. So 0 is, so to say, the best value you can get from bottom, because you get from the bottom and you want to get from something very negative to 0. Yep. Okay, so in a sense, then the idea is really simple, but yeah, really nice. Now, what is so important about this is not only is it a nice idea, it also has very nice properties. Because I mean, okay, we can do this. Who tells us now? So intuitively, one would say, or what I asked myself when I saw that the first time was, yeah, okay, it makes sense, but I don't see why the generator will learn P data. I only see that the generator learns to avoid creating objects that are not possible in the original distribution. Yeah? Because as long as the generator produces something that is possible here, how could the discriminator say that it's false? Okay. So when I saw that the first time, I didn't really believe that the generator really learns this distribution, only one that has the same support. So everything that is impossible here is also, or the other way around. So everything that he generates should have a strict positive probability here. As long as that is the case, I thought that that would be already enough. But it's better than that. So the objective again is this one. That was the function p. Okay. So a good way now to think about this is to say the discriminator plays first. And it's exactly like this in the training procedure. So the discriminator plays first. So the discriminator wants to maximize this. This is what we said all the time, okay? So we're looking here for a discriminator that maximizes this term. And now when we think that this discriminator is fixed, then what should the generator do? Then he should minimize this, right? So because the generator wants to make life for D as difficult as possible. Okay, so this is a min-max game, a classical min-max game. So that's the general objective. Now, one can here derive this term and look, what's the argmax for the D? So you can derive this term and look what is the optimal behavior for D, for the discriminator. And if you do this, then you find out that for a specific generator, the optimal behavior would be to assign, for an instance, the following probability. The probability that you should assign is ideally is the true distribution, the true probability or the true density of this X over the sum of the true density and the probability that is reflected in this generator. Of course, this is a theoretical number. The discriminator neither knows the true distribution nor the other one. But from a theoretical viewpoint, that would be the optimal solution. And that would also mean that in the limit, it would converge towards something like this. Now, if you put this optimal solution for the discriminator into this formula, so you replace this d of x and this d with this formula, then you get that what the generator now should minimize so you get a new formula, and this formula should be minimized by the generator. And the formula that he should minimize is actually a very simple one, which is the Jensen-Shannon divergence. This is closely related to the KL divergence. Okay. So what the generator should do, he should minimize, or he will minimize the Jensen-Shannon divergence between the true distribution and the distribution that he generates. So ideally, he makes this divergence 0, and this divergence 0 only if these two distributions are identical. In other words, the generator must learn, or his implicit objective will be what he will do. If we minimize this here with our training procedure, he will learn to minimize this discrepancy, and that will mean that his true distribution that he generates will be every time more equal to the true distribution P data without knowing P data and even without having a single instance available from that distribution. So that, I mean, that looks almost like a miracle, right? But this is exactly how it works. So that means in the global optimum for G, we have that these two must be the same. And what happens in this optimum if these two distributions, so this basically means, so if the generator is able to perfectly simulate the original distribution, then we have here P data over P data plus P data, because that will be the same. So we have P data, so the original density over 2 times that density. So it will be, so this discriminator, the best what he can do is to say, I don't know, 1/2 probability for any X. Okay, doing something like that then gets you 85,000 citations. Yeah.
And in real life, does this have like any kind of restrictions, or why doesn't people like use it to increase, for example, data or other type of models? Like to use data?
Yeah, they do. Yeah. I mean, you can use this directly for data augmentation, but the problem is, of course, I mean, it depends for what do you want to do it. So, okay, so yes, of course, there is some kind of restriction. So this P data here is, of course, in reality, often a bit limited. So if you have a data set of only 100 data from sources, so maybe there is a true P behind this. So the point is that in reality, you don't really have access to this, but you only get, I mean, you get some data set, which is this. That's already finished. But of course, there are now many data sets, many distributions that that are compatible with this sequence. So what this here assumes a bit, or what proof assumes, I didn't mention this, but what this assumes is that you have really an infinite number of samples from this distribution available, at least in the for the discriminator, right? And in practice, this is not the case. In practice, you have 100, 200, or maybe more. But if you have really a huge number, like hundreds of thousands of samples, then this will work. You can always use it. No, I mean, even if your database has only 100 entries, you can use it. But the point is that then maybe you approximate a distribution that is not really this one, but another one that is compatible with this, but not the true one.
Okay.
So what you then get is you converge to a generator that produces this type of data, and it would be very plausible that that generator would generate exactly the data that you had in the beginning. But it doesn't mean that it's really the true distribution. So for that, you need that that the data you have available is already somehow very huge. Remember that like 20 minutes ago, I said what you would do in PyTorch is that you take this finite number of data points and you create an iterable data set from that. So you create now an infinite sequence of training points, but you, of course, at some point will start repeating the same points over and over again. And what this here assumes theoretically is that you don't do this, that you always sample directly from the true distribution. And not from, this is a bit like in bootstrapping, where you are bagging, where you say, I pretend that my true distribution only has these values here. Okay, so that makes that the approach maybe is a bit, if you have few data points, and you want, for example, to use it for label data, then you start maybe assigning. So it's a bit, you get maybe somewhat questionable data points for which you're not sure whether that is really so true. This probability goes to 0 as the number of samples you have goes to infinity. But if you have very many instances already before, then you don't need to generate technique. Okay. But still, it's useful, and specifically here also for the if you don't care so much about labels, but just say I want to generate images, for example, and it's a very nice mechanism. Okay, what? Okay, so here, this is the Ian Goodfellow paper. He has already also written one of those very famous books on deep learning. So I have it here for your consideration, but this is relatively easy to understand, I would say, compared to the state-space model. So next week we talk then about variational autoencoders that also apply this idea of generative models, but then we talk about the conditional probabilities. Okay, so then we will look how can we generate basically sample labels for a given axis. Okay, very nice. Let's have lunch.
But if, in any of the remaining classes, are we going to maybe see graph neural networks?
Yeah, I thought about it. And actually, just today I thought about it, but I think we're not going to have the time because I mean we just have 2 classes left. So next week we have variational autoencoders are very important. So we definitely must look at that. And then we only have one left for either diffusion models or graph neural networks.
That's right.
I tend to diffusion models because graph neural network are essentially, I mean, we have talked about encoders, we have talked about transformers, and really just how do I use these techniques of encoders to have an embedding for graphs. So if I have a graph, how do I put it into a vector? This is mainly an encoding, and we have talked about that already. So I'm more inclined to talk about diffusion models. Need